Chapter 5, Section 5.3, Trigonometric Functions of Any Angle. The objectives in this section include: use the definitions of trigonometric functions of any angle, finding reference angles, using reference angles to evaluate trigonometric functions, and learning how the plus and minus sign affects the values of trigonometric functions, which is related to finding reference angles. Let's begin with some new definitions of the 6 trigonometric functions. The difference here between the right triangle definitions and these, they're equivalent, but they are different. Here, instead of starting on the positive x-axis and sweeping at an angle in the positive direction, we now make a right triangle, always form the right triangle by drawing a perpendicular bisector to the x-axis, and that defines a right triangle. Given that we have a right triangle, this length here, since it lies on the x-axis, will be the x length. The height here, the length of this segment, is given by the y coordinate. So the x and y coordinate of point P here, terminal point of the ray defined by the angle theta, is now x coordinate, length of side of triangle, and y coordinate, which is the height of the triangle here. And then this is still the hypotenuse of the triangle, but it is now r, the radius of the circle. So we have sine theta to be defined y over r. Notice if this is theta, y over r still means opposite over hypotenuse. The cosine is defined to be the x-coordinate of point P divided by the radius of the circle. And that still is consistent with before. Given angle theta, x is the adjacent and r is the hypotenuse. And all 6 of these definitions still are equivalent to the right triangle definitions in the earlier section. I'm going to look at the first 4 examples together as a whole and discuss what is going on. With example 1, 2, 3, and 4 here on the PowerPoint slide, what we are doing is looking at what's called the unit circle. This is the unit circle. Unit circle always has radius equal 1. And that's what means unit. Unit circle, circle of radius 1. Therefore, this distance here is 1. This distance here is 1, this distance is 1, and this distance is 1, since it forms the radius of the circle. So notice what happens here in the definition of these trig functions. Since r is equal to 1, sine is just the y-coordinate. Cosine is just the x-coordinate. Tangent's the ratio of y to x. The cosecant is 1 over the y, the secant's 1 over the x, and the cotangent is x over y. Which is why in the previous PowerPoint section I said always think sine means y and cosine means x. Later in the problem section I'll do an example of a point P which is not on the unit circle, which means r is not 1, and now we'll have to invoke here the Pythagorean theorem, and the problem becomes a little bit more involved, and these definitions are more crucial, and sine will not just be the y-coordinate, it'll be y divided by r. Okay? So keeping this in mind here, moving to the first slide, we have evaluate, if possible, the cosine function and the cosecant function at an angle of 0 degrees, which is also 0 radians. That means we're right here. So the initial and terminal side of the ray is here, and we do not rotate at all, so the angle is 0. Since r is 1, then, sine is just the y-coordinate, which is 0, cosine is the x-coordinate, which is 1. We are asked for the cosine, which is the x-coordinate, so that's why we get 1 here. And we are formally showing here that the radius is 1. That's where that is coming from. Now the cosecant is the radius divided by the y-coordinate. Again, the radius is 1, but the y-coordinate here is 0, and that's why the cosecant is not defined there. In a similar way, moving over to example 2, Here we're asked to find, evaluate if possible, the cosine function and the cosecant function at 90 degrees, pi over 2. So that puts us here on the unit circle. X is 0 and y is 1, and of course r, the radius of the circle, is also 1. So in this case, cosine, well, that's just the x-coordinate here at pi over 2. The x-coordinate at pi over 2 is 0, and the cosecant is the radius, which is always 1 here in the unit circle, divided by the y-coordinate. The y-coordinate is 1, so the cosecant is 1. So both trig functions there are defined. In example 3, we're asked to find, now here we have a rotation at pi. So we're going to rotate from the positive x-axis all the way around like this, 180 degrees, or pi. That puts us at the coordinate -1, 0. And we're asked to find the cosine and the cosecant at that value. So proceeding as before, the cosine's the x-coordinate, which is -1. There we go. We formally show that the radius is 1, but you can just pick off the x-coordinate because you're on the unit circle. And the cosecant is not defined there because that involves division of the y-coordinate, which is 0. So not all 6 trig functions are defined at various locations, so you have to actually check to see what is defined and what is not. Moving on to example 4. Evaluate if possible, again the cosine and the cosecant, now at 270 degrees or 3 pi over 2. So we're now rotating from the positive x-axis all the way around here to the negative y-axis, as the picture shows. The coordinate there is 0, -1, because, again, radius is equal to 1. That's why it says, let us choose p to be 0, -1. In other words, they are making this be on the unit circle to simplify matters. And that's not always the case, and that's why I'll do an example in the problem area where point P is not on the unit circle, so the radius will not be 1. So again, at this coordinate here, 0, -1, the cosine's the x value, which is 0, and the cosecant is 1 over the y-coordinate. The y-coordinate's -1, so the reciprocal of that is -1. Okay. Now, in trigonometry, it matters greatly where you are, because where you are governs the plus and minus signs in the quadrants. So as you know from basic algebra, in quadrant 1, all values x and y are positive. In quadrant 2, x is negative, y is positive. In quadrant 3, both x and y are negative. And in quadrant 4, x is positive, y is negative. Now, this slide shows the signs, S-I-G-N, the plus and minus of the trigonometric functions. Since x and y are all positive, since x and y coordinates are all positive in quadrant 1, all trig functions are positive there. In quadrant 2, it says only the sine and the cosecant are positive, because sine and cosecant involve only the y-coordinate, and that's positive. Yes, they involve r, but r is always positive. It's the radius of the circle. So only the sine and its reciprocal, cosecant, are positive in this quadrant. In this quadrant, the only trig functions that are positive are ones that involve both x and y. So that's why it says here, in quadrant 3, the tangent and the cotangent are positive. And in quadrant 4, only trig functions involving just x are positive. So that would be the cosine and secant are positive there. Now, one way students remember this is to say all S for students, T for take, and C for calculus. All students take calculus. All trig functions are positive in this quadrant. Only the S function, the sine and its reciprocal. Here, only the T function and its reciprocal, tangent. And here only the c function, cosine, and its reciprocal are positive. Since all students don't take calculus, you could, if you wish, say that all snakes tease chickens. ASTC, which is more true than all students taking calculus. Okay, let's take a look at reference angles and how they are defined and how we use them. Definition of a reference angle. There are 4 quadrants. In the first quadrant, if you rotate in the first quadrant, then that angle theta that makes that rotation is its own reference angle. If you're in quadrant 2, as the picture shows, you rotate from positive x-axis to quadrant 2, then the angle formed between the terminal side of the angle and the x-axis, always the x-axis, never the y. This smaller angle here is called the reference angle. And if you rotate to quadrant 3, again, the angle between the terminal side of the angle of rotation and the x-axis is the reference angle. And in quadrant 4, your reference angle is, again, pinched between the terminal side of the angle and the x-axis. Now, a little tricky here, when you're in this quadrant, to get the reference angle, you take 180 degrees, or pi, and then subtract the given angle. That will leave the amount that's here. So it's 180 or pi minus the given angle. In quadrant 3, notice that the order has swapped because your angle is larger than 180 degrees, than pi. So if you take the larger angle here minus half rotation, it'll give you this amount right here. And that's why the subtraction there is backward. Okay. Another way students remember this is the bow tie, that in quadrant 1, for an angle of rotation like that, the right triangle is drawn perpendicular to the x-axis. If you rotate all the way over to quadrant 2, like that, and again, perpendicular to the x-axis forms your right triangle. And if you rotate all the way over to quadrant 3, then again, perpendicular to the x-axis, and if you rotate to quadrant 4, again, the right triangle is formed by perpendicular to the x-axis. So this shows that the reference angle, here's the reference angle for quadrant 2, here is the reference angle for quadrant 3, here is the reference angle for quadrant 4, and the reference angle in quadrant 1 is always itself. Never ever draw a triangle that is this way towards the y-axis, always perpendicular to the x-axis. So sometimes that can help. Example 5. Find the reference angle for each of the following given angles. Okay, theta equals 210 degrees. So first thing you got to do is you got to draw a picture there. Best thing to do in trig is draw a little picture. It's worth an awful lot. 210 degrees, so past 180, that's about 210. This would be 270. There you go. The reference angle is right here, pinched between the terminal side of the angle and the x-axis. So to get that reference angle, we take the given rotation, 210 degrees, and subtract 180 degrees, and that gives us this little bit in between. So that's why it's the given angle minus 180. So the reference angle is 30 degrees. You can also think of 30 degrees as the amount by which this rotation exceeds a half rotation. It exceeds it by 30 degrees. So 180 and 30 is the given angle of 210. Now the given angle, 7 pi over 4. Okay, so we can think of 7/4 as 1 3/4. So 7/4 pi is 1 pi plus 3/4 of pi. So that will put us, here's 1 pi, and 3/4 of that would put us over here. So there's your given angle, theta, right there. And then the reference angle is right in here. And you can think of the reference angle as, if you've already gone through a rotation of 7/4, how much more would you need to rotate to complete a full 2 pi? And that would be 1/4 or pi over 4, because 7 pi over 4 plus 1 pi over 4 yield 2 pi. So pi over 4 plus 7 pi over 4 is 8 pi over 4, or 2 pi. Yeah. So this is your given angle here, and this is your reference angle. I like to label it theta ref, is your reference angle. According to the directions in the PowerPoint, we take 2 pi, which is a full rotation, subtract off the given angle, and that'll leave the amount left over right in here. That's why the subtraction works in that direction. Okay, lastly, we got theta equal 3.6 radians. Where is 3.6? So we have to think here that 3.6 radians, well, pi 3.14. So we're a little bit more than a half rotation. We're over there in quadrant 3. So to get the reference angle, which is right in here, we'll take the given angle and we'll subtract pi. So that's what we do right here. The given angle minus pi would be the reference angle right there. Okay. Go on to what happens when you have an angle that's greater than one rotation, greater than 360 degrees, or you have a negative angle that's also very large, more than one rotation. What do you have to do? So it says here, you got to find the coterminal angle first, draw that, as I was doing already in standard position, and then figure out the reference angle from there. So let's put that into practice. Here's a large angle, 665 degrees. So for 665 degrees, think about that. All the way around, that's 360. So this is a rotation that's very, very large. You take 665 and you subtract a full rotation, you end up with 305, which means the given angle is a full rotation. It's almost 2 rotations. That's where you end up. So there's the given angle is 665. The reference angle is always right here, always pinched between the terminal side of the angle and the x-axis. So you can think of it as 305, this is your coterminal. Which I believe they're calling alpha here in the PowerPoint slide. Then the reference angle is here. If you've gone 305, how much more do you need to rotate to complete the rotation? That's another way to look at the reference angle. So the reference angle, according to the prescription in the PowerPoint, is a full rotation minus your given angle, which is in standard position. That's the 305 degree angle. That means just going around the circle to here and stopping. So this is your 305 degree, that's alpha. That's your coterminal angle. So reference angle right there. So 360 minus 305, and that's where they got 55 degrees there. If we have a 15 pi over 4 angle, okay, how big is 15 pi over 4? So you can think of 15 fourths as 3 and 3/4. So 15 pi over 4 is going to be 15 pi over 4 will be 3 pi plus 3/4 pi. Okay, well 3 pi count in terms of pi, 1 pi, 2 pi, 3 pi, and now we need 3/4 of pi. So 3/4 of that's going to put us over here in the 4th quadrant. It's a huge angle. Okay, the reference angle is still right here, pinched between the terminal side of the angle and the positive x-axis. Okay, so we need to get the coterminal angle first. So if we take our given angle, let's make room there. So we have 15 pi over 4 and minus 2 pi, so let's write 2 pi as 8 pi over 4. That's 7 pi over 4. That's our coterminal angle. That means that we have stripped off one of the rotations and we're just talking about this angle here. So we took off the full rotation and alpha is just starting here and rotating the quadrant 4. This is still the reference angle right here. So to get the reference angle, we're going to take 2 pi, full rotation, minus the given angle alpha, the coterminal angle alpha, and that's what we show right here on the slide. 2 pi minus 7 pi over 4 with common denominator yields pi over 4. So this amount here is pi over 4, and this amount to there is 7 pi over 4. Once again, notice 7 pi over 4 plus pi over 4 is 8 pi over 4. That's a full rotation. So you can always add up to think about the reference angle rather than subtract. Okay, lastly, we have a negative angle here. So we have negative 11 pi over 3. So that's our given angle, negative 11 pi over 3. So what we'll do, think about that. If we add 2 pi to that, negative 11 pi over 3 plus 2 pi, let's write that as 6 pi over 3. That's going to give us still a negative angle, negative 5 pi over 3. That's still no good because alpha has to be a positive angle. So take negative 5 pi over 3, add another 2 pi to it, until you end up with the positive angle, which is now pi over 3. That's now alpha. Now, where are you here? Your coterminal angle is a quadrant 1 measurement. So in other words, negative 11 pi over 3, 3 and 2/3 pi, 1 pi, 2 pi, 3 pi, and 2/3 of pi. There it is. So there's negative 11 pi over 3. We took that and we got the coterminal angle. So the coterminal angle is pi over 3. That's this one, alpha, pi over 3. But in quadrant 1, where we are, the reference angle is the same in this case as the coterminal angle because we're in quadrant 1. So that's why we have the reference angle here in the slide being pi over 3. Okay. Let's take a look at using reference angles to evaluate trigonometric functions. Okay. The values of the trig functions of a given angle are the same as the values of the trig functions of the reference angle, well, except where you are, in other words, what quadrant you are in, because the quadrants have a plus or minus sign dependent upon which trig function you are looking for. So what it's saying is that we look at the reference angle, we get the trigonometric value, then we look at where we are, what quadrant we're in, and perhaps adjust for a plus or minus sign if need be. It's saying more of the same here. Find the associated reference angle and find the trig value and then adjust it for the plus minus sign. Putting this into practice is always the best way to proceed. So here we have example 7. Let's use reference angles to find the exact value of sine 300 degrees. Okay. The reason why a reference angle is needed in the first place is this angle is larger than 90 degrees, so you're outside of quadrant 1. That puts you in the 4th quadrant. Well, first find the reference angle. There's no coterminal angle here because this is within one rotation. If it's a larger than one rotation, you have to first find the coterminal angle and then the reference angle. But this is within one rotation. So we can proceed immediately to how to get the reference angle. Since we are in quadrant 4, we'll take a full rotation minus our angle, and that'll be the reference angle. So now, what do we want? We want the sine. Okay, so the sine of 60 degrees is root 3 divided by 2. But the given angle is 300 degrees. So you have to look at in the fourth quadrant. Here we go. In the fourth quadrant, only the c function is positive, cosine and its reciprocal. The sine is the y-coordinate, which is negative in that quadrant 4. So we have to adjust with a plus minus, in this case a minus sign on the value, because of the quadrant that we're in. See, the sine of 60 is quadrant 1. The reference angle is always quadrant 1. It's always a positive value. But the given angle puts us in quadrant 4. The trig function being sine, that measures the y-coordinate, and the y-coordinate in quadrant 4 is negative, and that's why we have a minus sign there. Say, for example, we were doing the tangent, and the tangent involves y and x. And in the fourth quadrant, y and x, y is negative and x is positive, so again that ratio would be negative, so we'd have a minus sign on there. The value would be different than root 3 over 2, but again the trig function would be minus. That concludes section 5.3.